Yeah, okay. I think we start now. So welcome to the second session in this afternoon and the last one today. We are very happy to have Chihiro Sasaki from University of Wrocław here, not here in person, but here online, and telling us about parity doubling in cold and dense QCD.
Okay, thank you very much. I'd like to thank the organizers for invitation to the workshop, and then please accept my deep apologies that I couldn't be there, but this is not my fault because my residence card is not ready. Okay, all right. Okay, so here's the outline. I would like to present something very special, interesting, and then also very general model-independent phenomena at finite density, chiral mixing. And another type of chiral mixing was already introduced and then discussed a little bit by Tatiana on Monday, but this chiral mixing that I'm going to talk about is totally different class of the mixing phenomena. And then you will see that this mixing is induced by Westermino-Witten action. So in a sense, this is a nice realization of axial anomaly at finite density. And why this is interesting? Because this mixing directly modifies the dispersion relations of vector and axial vector states. So therefore, the direct consequence is the deformation of the spectral function of those states at finite density. And as a natural application of this effect, I'm going to show you some results on dilepton production rates at relatively low temperature and high density, which is exactly the target domain to be covered by Hades experiments. And the part 3, the last part, is devoted to in-medium broadening of those spectral functions due to the many body effects. And when you look at the rho meson, rho omega sector, especially rho meson, empirically we know there's a number of the rho nucleon resonances which modified quite a bit the rho meson spectral function at finite density. And then what's interesting is that, in the presence of such a new phenomena, chiral mixing, how the signature would be screened. If it would be screened, actually it would be screened, but the question is to what extent. And now, when you look at the fine meson spectral function in medium, and what's important is the property change of kaon and anti-kaons. And then I'm going to show you a pretty new result on this spectral function for phi, and then corresponding potential signature is seen in the dilepton projection rates. Okay, the motivation, I think it's more or less clear. So namely, what would be the signature of chiral symmetry restoration to be measured in dilepton production rates in heavy ion collisions? So far, we have seen the quite substantial modification of the rho meson spectral functions in hot and dense matter, but the question is if it's related to the restoration of chiral symmetry. So if you look at only the modification of vector spectral function, this is always incomplete because the vector quantity itself is not the order parameter. So therefore, the right strategy is to look at not only the vector states, but also axial vector states. So in the presence of matter, axial vector mesons can show up actually in the vector spectrum. So this phenomena is what we call chiral mixing. So therefore, it's just in a sense sufficient to look at the in-medium vector spectral function and still as we are able to learn the modification of axial vector meson according to the partial restoration of chiral symmetry extracted out of the in-medium vector spectral function. So this by itself is very intriguing. Okay, so this is in a sense my summary slide. So if you are in a medium, but the temperature is far below the chiral crossover, and then your chemical potential is also far below the chiral crossover, and then this is a typical the shape of the vector spectral function. So this is the rho meson peak, and then this a little shorter appears due to the chiral mixing or parity mixing, which was discussed on Monday by Tatiana. So this mixing effect is nicely implemented in the form of low energy model independent low energy low temperature theorem by Day, Eletsky, and Yoffen. And then this type of mixing has been extremely well studied. And then what will happen when the chiral symmetry gets restored? So this is the result shown in the red curve. So the peak is associated with the raw meson mass, and then the second one is the contribution coming from the axial vector meson. And then toward the chiral symmetry restoration point, the raw and N1 masses should be closer to each other. And then when the symmetry is restored, and then the spectral function has just a single common maximum, not anymore 2 peaks or 2 bumps. Okay, and then at this point, the vector axial vector mixing, chiral mixing is resolved. So it's completely gone. So this is the situation if you have hot and dilute matter in the presence of chiral mixing. And then how it evolves as a function of T or mu toward chiral symmetry restoration in hadronic phase. So, but as I said, there's another type of the chiral mixing induced by either Chern-Simon term or the Wess-Zumino action, if you prefer 4-dimensional theory. And this is totally new because nobody has considered that. And you will see shortly that the different type of mixing induced by density drastically modifies the shape of the vector spectral function like this. Now, the characteristic 3-peak structure appears. So one is associated with the longitudinal polarization of the vector, and then the very left one is associated again with the vector states but transverse polarization. And then the last one, very right hand side, this is the axial vector states with transverse polarization. Okay, so such a superposition of 3 different polarization and different parties, this such a structure typically appears in the cold and dense matter. The question is how much such a structure change will be related to the partial restoration of chiral symmetry. So this is the main the issue to be presented in the talk. Okay, so our study was motivated by a holographic paper. The paper came out in 2007 by Domokos and Harvey. So they started with the bottom-up holographic QCD approach at a finite density. So they have introduced extra U1 symmetry associated with the density and corresponding barium chemical potential in 5 dimensions. And then they have deduced the 4-dimensional effective action in that form. So we have the conventional terms, pion kinetic term, mass term, and then raw meson and A1 meson kinetic terms and corresponding mass term down here. And then the last term. So this is new. So the last term in red is exclusively coming from the Chern-Simon term they started with in the 5-dimensional theory. And so here ijk runs from 1 to 3 without 0. So therefore, mathematically now it's clear that this term modifies only the transverse polarization, not the longitudinal polarization. And but the dispersion relations for rho and A1 states, they are in that form modified quite a bit. Okay, so at the moment, C representing the mixing strength is treated as a parameter. And then I'm going to come to the issue about the actual size of this mixing parameter. But for the time being, let's take two numbers. One is given in red, C being just 1 GeV. This is, by the way, the preferred value by them in their following paper. And then another illustrated value is 0.5 GeV. And then you will see those dispersion curves in P0 energy and then 3 momentum plane. So this one is for the raw meson or vector mesons, and then this one is for axial vector mesons. And as I said, green one in both, they are totally unmodified, unaffected longitudinal polarizations of raw and then A1 states. Okay, all right. Accordingly, the spectral function should be modified, right? Because the dispersion relation is now modified quite a bit. So again, as an illustration, let's take 3 momentum being just 0.5 GeV. And then when you look at the corresponding numbers in the dispersion relation, so the upper 3 lines are corresponding to the axial vector states, and then lower 3 lines correspond to the vector states. And okay, so 3 momentum being 0.5, and then we have, so first of all, longitudinal polarization is unmodified, so therefore we have the single peak at the vacuum raw meson mass, right, 770 MeV. And what about transverse polarization corresponding to the blue one, and then the sort of the lower maximum or lower bump is associated with this the immediate modified the mass of the transverse polarization of vector states, right? So this is roughly 0.4 or a little bit below sorry, a little bit about 0.5. No, below 0.5. Okay. All right. And then what about another one? So this corresponding to the transverse polarization of A1 states, and then look at this the value on the red curve. Okay, I have chosen C being 1 GeV. Okay. Okay, so therefore 1.5. So indeed, you will see 2 bumps according to the modified dispersion relations. And then what we see in the end is, of course, the average over those polarization, right? So two times transverse and then 1 longitudinal divided by the total number polarization 3. So this is given by given in this red graph as the level average. So therefore, so characteristic the structure, you will see that the 3 sort of maximum. So your spectral function is not anymore Breit-Wigner, but it's rather bumpy. And then, but we clearly see the modification of transverse raw meson, but also the modified the transverse polarization of axial vector meson. And then clearly we see the effect of A1 meson mass here. Okay, now, of course, everything depends on the strength of the mixing parameter C. So how to estimate in a reliable fashion? So for this, we started with a rather conventional approach, 4-dimensional chiral effective field theory approach. So namely, instead of Chern-Simon term, equivalently, we can start with Witten action, right, plus a non-anomalous term in the chiral Lagrangian. And when you look at the major the terms, including omega field operator rho and N1 as well, and then you will find such a term. Okay, now let's make mean field approximation here. So conventionally, when you take like a U-cover theory applied to nuclear matter property, and then the 0th component omega field gets condensed because of the same quantum number. This is identified with just a net baryon density proportional to density. And those numbers, omega nucleon coupling is known, omega mass is of course known. So therefore, when you put this omega 0 formula in terms of those known parameters depending on density back into our Wess-Witten term, then make a comparison between those holographic one and this one, the conventional one, and then you can immediately extract the formula for the mixing string C. So this is proportional to density, because omega 0 is proportional to density, and then all those parameters are empirically known. And when you put the numbers into those parameters, and you will get 0.1 GeV at the saturation density. So this is 1 order of magnitude smaller than the prediction from ADS CFD by Tomokos and Harvey's paper. They predicted at exactly at the same saturation density, extremely strong mixing mixing value being 1 GeV. And then when you come back to the dispersion relation, this corresponds to this at the lower one, right? You see there is a weird the curvature, weird behavior in red, and then this leads to some instability into the system, and then they conclude that actually within their holographic approach, nuclear ground state is a state with vector condensation. But of course, this is odd because we know empirically that this is not happening in our nuclear ground state. So the natural question is why they have estimated this coupling so large. So personally, I have not done any concrete calculation, but I can make a speculation. So presumably, this is a large NC artifact. So in large NC, as typically done in those holographic calculations, all higher lying states, they appear not as resonances, but just well-defined states described by delta functions. So the same situation can be seen in the description of well-known vector meson dominance in the context of like a Sakai-Sugi model, top-down holographic approach. So therefore, I presume that extremely strong mixing parameter in the holographic approach contains not only the lowest omega meson, but also contains just all the rest, the powers of omega meson contributed significantly. Okay. On the other hand, in reality, those higher lying states, that all resonances much broader, heavier, they should be integrated over, integrated out. And then this presumably the reason why we ended up with the one order magnitude smaller mixing parameter. Okay, anyway, it looks the number 100 MeV at the saturation density seems to be rather realistic one, right? And then you see the, I mean, when you take 5 times bigger the strength denoted in blue colors, still, I mean, you see slight, in a sense, slight modification compared to green one. Green ones are unmodified one without mixing. So therefore, when you put the 0.1 GeV as a mixing parameter, and then you may think there is no presumably the impact. But however, the point is that the mixing parameter is directly proportional linearly to density, and then what would happen when you increase density. So this is just the partial restoration chiral symmetry. Okay, so in the argument so far, the missing piece is such a potential effect coming from the partial restoration of chiral symmetry. Okay, just to motivate you, let me once again show you the dispersion relations in the presence of mixing, but now expanded for small 3 momentum, P bar. Okay, so the point is that the mixing effects is always appearing together with such a mass difference between the parity partners, A1 mass and the raw meson mass. Okay, so therefore the anticipation is that when the chiral symmetry gets restored gradually, and then effectively this mixing effect will be enhanced. So therefore, the hope is that such a mixing effect is also closely related to the potential signature of chiral symmetry restoration. Okay, good. So far, everything just the super general, just based on the relevant symmetry in your system at a finite density. But to see, I mean, to check, to verify what I mentioned, that requires some concrete model calculation. Okay, so for this, we need to carefully evaluate in medium mass difference between those parity partners and in medium strength, this parameter C as a function of temperature and chemical potential. And for this, let's take sort of generalized version of Valechka model, quark nucleon hybrid model, which we have developed here in Wrocław, and recently. The model has been confronted with the neutron star observations like tidal uniformability, solar mass constraint, radius from NISA, and whatever, so on and so forth. And so therefore, the model parameters that appears in our quark nucleon hybrid model are perfectly fixed. So everything just consistent to the neutron star matter properties. Okay, so here's the result. So essentially the mass difference between two parity partner is proportional to the order parameter. So in hadronic language, this is the pion decay constant, and then microscopically, this is of course pure vacuum condensate in the medium. Okay, so delta M normalized by the vacuum value of the same quantity is given in red. Okay, this is naturally decreasing. Okay, by the way, this was computed at the relatively low temperature, 50 MeV, and then at this temperature, the model does not yield any the true phase transition. Everywhere just crossover. So we have only the kind of crossover. Okay. All right. So see the mixing parameter, and then, as I said, so this is proportional to the condensation of the zeroth component of omega field. So this can be without any problem, can be computed as a function of chemical potential for fixed temperature. Now this is given in blue, okay? And when you look at the inflection point of derivative of the order parameter, so sigma is just a pion decay constant in medium, the order parameter, and then you will see the 2 times of the bump. And then the first one is associated with, in a sense, the remnant of nuclear liquid gas phase transition. And the second one, in a sense, a little bit stronger one, is naturally identified as the chiral crossover. And then, so therefore, a little bit beyond the 1 GeV in baryon chemical potential is the pseudo-critical chemical potential. And then this the critical value is in terms of the density is roughly 2.5 times the nuclear saturation density rho 0. So this is not a crazy number. Okay, all right. So this is some equations, but a very general one. The vector current correlation function now decompose into the longitudinal component and transverse component in terms of the coupling strength to the current, and then the mass, energy S, and then the V, dA, they are representing just conventional the propagator inverse, including the mass and the decay width. Okay, and then since we consider the situation in the presence of mixing non-vanishing C parameter, you see clearly that only the transverse contribution in the vector spectral function gets modified quite a bit like that. Okay, and so this is a very general formula for the vector spectral function, vector current correlation function, and then in principle, the masses and then decay width that appears here and there must be understood as immediate modified version of masses and width. But technically, it's really complicated to put all the such a medium effects. So therefore, just for an illustration, let's make the following approximation. Of course, I perfectly admit that this is drastic one, but it will be improved shortly. Okay, so first of all, we assume that the modification appears only on axial vector states. So therefore, we can just assume that the rho meson mass is not changed at all. The rho meson decay width is not changed at all. So only the axial vector quantities are changing as a function of chemical potential or temperature toward the chiral symmetric restoration. This is the first very drastic approximation. And then we set the 2 correlators, axial vector correlators, equal to the vector current correlators at the chiral symmetric restoration consistently, and according to the following the requirement. So in order that 2 expression becomes at least mathematically identical, the immediate version of the decay width for A1 should be, at the end of the day, identical to the rho meson decay width. And then according to the first approximation that I made, at the chiral crossover, our A1 decay width is equal to, almost equal to the vacuum rho meson decay width. So this is the kind of setup to see the influence of the chiral, the mixing parameter C. Okay, here's the result. The spectral function calculated at the same temperature. All right, so look at the upper 3 figures. So this one was computed extremely low chemical potential, namely far away from chiral crossover. So essentially we see nothing, no influence from the chiral mixing. So this is very natural. And the middle one, some intermediate chemical potential, not far away from chiral crossover. And then the last one, the right figure, was computed exactly at the chiral crossover chemical potential. And then we see clearly the deformation of the vector spectral function through the chiral mixing, as we have seen already. And then in a sense, characteristic 3-peak structure becomes evident in the rho meson spectral function. And then it's quite constructive to repeat the same calculation, but in a different scenario. So namely, the upper 3, the figures are computed with the chiral symmetric restoration, and the lower one can do the similar computation without chiral symmetric restoration. So here I have assumed that the parameter C, mixing parameter, is changing as a function of chemical potential, but the delta M or other parameter is kept to be just constant. It's meaning that the pion decay constant never becomes vanishing, meaning that this corresponds to a scenario without chiral symmetry restoration. And then at the maximum chemical potential at mu C, you see some slight difference compared to the longitudinal one without any modification, but essentially, I mean, such a difference is, negligible. So essentially, we see nothing. So this is nicely illustrating that what we have anticipated in the beginning here, that indeed, when the chiral symmetry gets restored, the effective mixing effect becomes enhanced, and then so therefore, such a drastic modification of the vector spectral function is the signature of chiral symmetry restoration. Okay, the same quantity. I mean, now I have put omega as well, but I mean they appear in any case so close to each other, even in matter-free space. The raw omega spectral function at the same temperature for various distance from the chiral crossover. For low value of this, the delta M ratio corresponds to, in a sense, the situation, this one at low chemical potential, very far away from the chiral crossover, and then the closer to the chiral crossover in the middle in green, and then you see some deformation, and then exactly at the chiral crossover chemical potential in red, you see such a bumpy structure. Now, this is the superposition of not only such a bumpy structure coming from the raw meson, but also coming from the omega meson, as well as their parity partners, epsilon vector mesons. Okay, and then the characteristic 3-peak structure is best preserved in the sector of fine mesons. Okay, so let me emphasize once again. So look at the red one. So here you will see the maximal effect coming from the chiral mixing, and then this middle one corresponds to the longitudinal polarization of fine meson, and then according to our current setup, this is unmodified. Okay, so therefore the peak appears exactly at the 1.2 GeV, and then this left one, this is a medium modified fine meson, but with a transverse polarization. This is shifted to the left according to the given dispersion relation, which we have seen already a couple of times. And then this one is the transverse polarization of axial vector states. And then according to the PDG booklet, this is called F1 state. Okay. All right, so, and then now we are ready to compute the director rates at the same temperature, at the same chemical potential. This is computed at the chiral crossover chemical potential. And then this is integrated quantity, integrated over 3 momentum up to 2 GeV. Okay, and then you see the clear structure change also in the director rates, even after the integration over 3 momentum. So this is interesting, but of course, I have made an extremely crude approximation, namely, I totally omitted the immediate broadening of the raw meson decay width. This should be implemented anyway to say something firm. Okay, so this technically can be done. There's a bunch of the papers, bunch of studies in this context so far. So first we look at the raw meson spectral functions in the nuclear medium. So there's a set of the important raw nuclear resonances summarized in this table down here, but especially those 2 states, they are important one because they very strongly couple to the raw meson already in matter-free space. And the direct consequence of inclusion of those baryonic resonances is the strong level of mixing. So this is solid one is the vector spectral function at zero density. So therefore this conventional one computed at some finite 3 momentum. I don't remember what was the value of the finite momentum, but this is just matter-free space, the result. And once you introduce the finite density in the presence of those resonances coupled to vector mesons, and then such a level of mixing appears, and then so we cannot say anymore the raw meson peak where the raw meson peak appears. It's completely screened because of the strong interaction to baryon resonances between baryon resonances and the raw mesons. Okay, and then this such calculation was done first by Friedman-Filner in '97, and then afterwards Dargrab and his collaborators updated in a similar direction, introducing more baryon resonances in the same channel, in the raw meson channel, and then they have determined the corresponding coupling and some medium correction to the decay width and so on and so forth, with a comparison, with detailed comparison to the experimental data of the photon nucleus reaction. Okay, so therefore now the idea is implement all those the baryon resonances coupled to vector mesons and then repeat the computation as instructed in this paper. Okay, so here is the result. Excuse me, I forgot to include the vector spectral function, but this is already the dilepton production rates. Okay, so this must be compared with the previous one, this one. Okay, so unfortunately, but it's expected that the signals of chiral restoration, according to the vectors, the rho A1 mixing, is to large extent washed out, diminished by especially mainly by P-wave states. Okay, so this is a pity, but I mean this is as it is. So here I made, I have prepared the 3 different sort of scenarios or different options. So let me explain one by one. So first of all, the middle one in blue. So this is the scenario with chiral symmetry restoration. So what I have done? So what I have done is the following. So this was computed at the chiral crossover. So therefore, the axial vector meson mass is more or less equal to the vector meson mass, right? Not exactly the same because of this chiral symmetry breaking, but they are more or less the same. And so the next equality is, in a sense, my assumption. I just assume that even at the chiral crossover, the vector meson mass remains the same as in the matter-free space. So therefore, 707 MeV mass is kept in this computation. Only the axial vector meson mass dropped toward 770 MeV. And then the same, in a sense, trick was made in the baryonic sector. So the calculation includes both positive parity baryons and negative parity baryons, and according to the chiral restoration acting on parity doublers in baryonic sector, those masses should be more or less the same as well, right? And then again, just like the vector meson states, I have assumed that the lowest nucleon mass, the baryons with the positive parity states, have exactly the same mass as in the matter-free space. Okay. Okay, that way I obtain the curve in blue, corresponding to, in a sense, one option for the chiral symmetry restoration. And this is compared with the scenario without chiral symmetry restoration, given in green. And then, unfortunately, I mean, you see some the difference here and there, but the difference is not like one order of magnitude, so they are rather close to each other. Okay, now what about the first one in red? There is also a possibility that those the meson masses and then also nucleon the masses at the chiral crossover would be different from the value of matter-free space. So, for instance, so therefore, I mean this one was motivated by very recent study by Soo-Hong Lee and his collaborators in the context QCD sum rules, which were applied to the corresponding meson baryon correlation functions in terms of interpolating field operators with unbroken chiral symmetry. And then they have found that, for instance, the raw meson mass in the chiral symmetric world is smaller than the non-value 770 MeV, but it gets down to between 500 to 600 MeV. And then similar number was found for the nucleon and then I think also delta mass as well. Okay. And when you put, so when you take such an option, and then you will get the red curve. So in this case, if this is realized as the manifestation of unbroken chiral symmetry, and then the signal, the deviation from the baseline without chiral symmetry restoration, this green one is, extremely big, right? It's like even more than 1 order of magnitude. And then we may have, only in this case, we would have a chance to really say something about the chiral symmetry restoration in the context of dielectric measurements in heavy ion collisions. Otherwise, presumably, we wouldn't have a good chance. Okay, what about the fine mesons? So there's a significant difference from the situation in raw mesons. So namely, there are no apparent phi nucleon resonances. So therefore, the primary source of the medium modification of phi meson spectral function is the modification of kaons. And such a study on kaons, anti-kaon in nuclear matter was pioneered by David Kaplan and Nelson in the paper. The paper came out in '86. And then they have found, so they studied the property change of kaon and anti-kaons based on SU3 chiral Lagrangian approach plus mean-field approximation to introduce density effect. And then they have found such a dispersion relation, which are quite a bit modified. So the star means in medium mass for kaon, and then the second one is in medium mass for anti-kaon as a function of the vacuum mass of kaon. And then AK bar, there are some parameters, and then at the leading order in this the SU3 chiral approach, they are found to be identical and then also proportional to kaon nucleon sigma term corresponding to this chiral symmetry breaking, and the proportional to rho s. Rho s is the nucleon scalar density. So this, in a sense, like just a phase space integral. And BK, this is another parameter. And then in the SU3 chiral approach, this is identified as such a number, some precise number. Okay, so what's characteristic is the different sign here in front of the last term, plus and a minus. This is just opposite. And then the last terms both proportional to the net baryon density rho. Okay. So therefore, the masses as a function of density, kaon and anti-kaon, they behave completely different way. And then of course, how they actually behave quantitatively crucially depend on the parameters A and AK bar, and then BK as well. And then presumably, in order to have the more realistic description, we need to go beyond the leading order computation. And then the similar, so based on such an idea, in their paper, Jerry Brown and his collaborators in '97, they treated instead those, the B and A just as a free parameter. And then the result of the kaon production was confronted to the experimental data, low energy heavy ion collision, nickel-nickel collisions at the given the collision energies. And then they have extracted the preferred value for those parameters. And then they are now consistent to the low energy heavy ion collision data. So this is very nice. And then they have found that AK and then AK bar, they are actually different. And then also rather smaller than this the leading order estimate. And then BK was kept to be the same number. Okay, given those parameters, and now one can make a plot for the immediate mass for kaons. This is the upper curve. This is increasing as a function of density in the unit of saturation density rho 0. And then on the other hand, the immediate mass of anti-kaon, this is decreasing. Okay, so this is really substantial. And and then actually the sum of the kaon mass and an anti-kaon mass, this sum is actually decreasing as a function of density. So therefore, the threshold of the phi meson decay into kaon is of course it's shifted to the left in the spectral function, and then accordingly the decay width, in medium decay width of the phi meson in nuclear matter also modified. So this is such a density dependence constructed in their paper. So they have considered two sort of options. the first one given in this dotted one, so they have introduced only the medium modified kaon, the anti-kaon masses according to those two curves, but they have kept the phi meson mass being just a vacuum value. Okay, and then it's the medium decay width of phi meson is increasing as a function of density, but it's really interesting to compare with another scenario. So namely, one can further assume that the phi meson mass can also be slightly different from the vacuum value. And then they have assumed a kind of the Brown roll type scaling, but not significant reduction, but only, as far as I remember, just 5% reduction of the phi meson mass. And then you see the still the gamma phi is increasing as a function of density, but compared to the first scenario, this increasing is rather milder. Okay, now back to the spectral function.
Hiro?
Yes.
5 minutes left.
Okay, thank you very much. Okay, I'm almost at the end. The phi meson spectral function with such a medium modified the kaon anti-kaons and in the presence of the chiral mixing. Remember that the chiral mixing appears always in that combination. So the parameter itself and the three momentum p bar. Okay, so therefore the spectral function, even at the chiral crossover, the structure really depends crucially on your choice of three momentum. So those three figures are such a nice illustration. So this one with the three momentum being just 0.1 GeV, and then essentially you see nothing. And then the middle one was with the 0.5 GeV for the three momentum, and you start to see the deviation from the baseline. So this deviation is just a consequence of chiral mixing at the chiral crossover. And then when you put the three momentum being 1 GeV, and then you see, I mean, the modification is very evident. So therefore, this is I mean, they're telling us a nice message that the very careful binning in momentum, this should be at least bigger than 0.5 GeV. When you look at the dilepton data in the measurement and then the comparison to the data. Okay, good. All right, so given these things in mind, now I show you the dilepton rates, again, at the same temperature, at the same, the chiral crossover density, but now these rates are obtained after the integration of the three momentum over not from 0, but above 0.5 GeV. So low momentum contribution should be excluded because otherwise the signal of chiral restoration will be screened. So I have to consider three different scenarios. So immediate mass of phi meson remains the same as in the matter-free space, and then use, I mean, the two scenario between those two curves with and without chiral symmetry restoration. Well, it's not dramatically large, although we see some deviation, some difference here and there according to the mixing as expected. And but when you introduce slight reduction of the mass in the the phi meson by 5%, and then this the signature of chiral symmetry restoration gets rather dramatically large, and then according to the drop in masses, everything just shifted systematically to the left, and then this is the similar illustrative computation, assuming that the reduction of the mass of the phi meson is now the 10%. Okay, so this is in a sense the last one. There remains the theoretical option that I have presented the result with the mixing parameter, which was estimated under mean field approximation, and then mean field approximation. This is nice for the illustration, but of course, I mean, the several important physics presumably are omitted, and then in reality, the mixing parameter could be larger. And also another possibility is that the critical density could be higher than 2.5. Why not? So therefore, all such the different option or possibility can be nicely implemented into the following case study by changing the strength of the mixing by, let's say, 20%, corresponding to 3 times the saturation density for the critical density, and then the increase by 40% corresponding to 3.5 times saturation density as the critical density. All those numbers, as I must say, I mean, in a realistic, the range as a potential, the scenario of chiral symmetric restoration at large density at the low temperatures. Okay, and then of course, if you have such a lucky situation with the bigger, even slightly bigger mixing, and then the signal of chiral symmetric restoration, of course, gets enhanced here and there, especially. Okay, so here's a brief summary. So I have introduced the notion of the totally different new class of chiral mixing induced by density through meson-Witten action. And then this mixing exists at any density. So therefore, this has a crucial impact on the structure change in the vector spectral function, consequently direct-on rates. And then, so we are in a sense ready to offer immediate modified the vector spectral function to the experimentalist like Tatiana. We just started such a collaboration with her. So she and her, the students will nicely update their coarse-grained approach with the updated version of the spectral function in the presence of chiral mixing under the hardest acceptance. So this is going to be very interesting if we would see the signature of chiral symmetric restoration in electron rates. Okay, and then unfortunately I have no time to speak about another kind of the parity doubling the consequences in the nucleon sector in the context of neutron stars. Yeah, okay, so maybe if I have some other opportunity to speak about it, it can be presented elsewhere. Okay, thank you very much for attention.
Yeah, thank you very much for this very nice and clear talk. Are there questions or remarks? No questions? So did I understand correctly that the signal you found from the modification of the vector spectral function, they were washed out by the broadening of the row, but
yes,
you think that you can still?
Yeah, but the message on this the figure is that what you said is true. I mean, the signal to a large extent just washed out if the vector meson mass, the mass remains the same value as in the matter-free space. But actually, we do not know. Could be different. Could be lighter, as indicated by this QCD sum computation and also several other modern approaches. And then everything is just shifted upwards, and then the difference compared to the baseline in green is rather big, and then we would have a chance. But otherwise, presumably no. This is what I said.